Hey YouTube, what's up, Link? Welcome back to another episode of Coding Session, and today we're going to continue our discussion with the binary search trees. So I said in the last episode I'm going to try to find some problems on LeetCode so we can apply the binary search tree data structure and its algorithms. However, I'm going to more so just show you examples um, of the data structure and its common and useful algorithms, and if I find any problems on LeetCode involving binary search trees, I'll definitely make a video on those. But today we're going to create our own binary search tree and search for a specific node in it. So this example I'm going to show you, this is a non-ordered tree. If you watch the last episode, you'll see there's a way we build a search tree properly. But as you can see, our root is the top of the tree is 0. But since 1 is greater than 0, it should go to the right, but we put it towards the left. So this has no particular order. This is just an example. And we can still go ahead and perform the example we're going to show today, which is searching for a specific node. But first we need to define our tree node. And this is very similar to the examples on LeetCode problems, such as the invert tree in the last episode. So we got public class tree node, and data is just going to be whatever type of data we're putting in this. In this case, it's going to be a 32-bit signed integer, and the tree node left and right are going to be pointers to the root's child or children, if any. But if there won't be any childs or children, then this root will be considered to be a leaf. And then we have our constructor. We pass integer through it, set its integer, and then of course initially left and right is going to be equal to null. So this root is essentially going to be a leaf initially. Now if we hop over to our main, we will start our binary tree node root. Tree node root is equal to new tree node 0, so make a new instance of it. 0. And then we go to the left, it's going to be 1, and we go left again, which is 3, and then we go left left again, that is going to be 7, and this time we go left right, which is 4, left right left, and you kind of get the gist. And maybe I can somehow try to visualize this, so give me 1 second. Okay, so bear with me. This is going to be extremely ugly, but this is the visual representation of our tree here. Again, not properly ordered. So we got 0, we got left 1, left 3, and then left, which is 7, and then we go back up, and we do left right, which is 4, left right left, which is the 8 right here, if you can see my cursor, and then left right, which is the 9, and then we go to right, which is 2, and then right left, which is 5, and then right, which is 6. So this is our example tree, and we're going to we want to search through the tree to see if the node actually exists. So we can do this recursively. A lot of algorithms such as the in order, pre-order, and post-order are going to be, most of the examples you're going to see are recursive. So in this case, we want to take advantage of the traversals, and we're pretty much going to do the pre-order. And that is, we visit the root first, then we go to the left subtree and then the right subtree. So here is our base cases. If node's equal to null, the tree is empty, just return false. Of course, if it's empty, nothing's there. So, however, if the data or the current root we're on is the key, return true, that we found the key or the node we are searching for. If not, we want to go ahead and recur on the left subtree. So call recursive call. If node exists, node.left key, and if res1, then we return true. In this case, we would have successfully found it in the left subtree. If it's not found on the left, we'll want to recur to the right subtree, and this is result number 2. And then the recursive call node exists node.write the key, and then we just if found, then we simply return res2, whichever that may be, true or false. So this is a recursive, and it's used in pre-order. This is the root, then the left, then the right. So I want to go ahead and try to find 4. So if I go ahead and run this, it's going to say 4 was found in the tree. But if I put like 4, let's say 22, which is not in the tree, it's going to say it's not found. So this is pretty much how you define a binary search tree. The tree node itself, public class node, a tree node, int data, could be any type, could be a string, could be a char, could be an integer, could be a double, could be a float. And of course, you want 2 tree node references or instances, left and right, which are going to be your leaves, or no, I'm sorry, you're going to be your children to that root. But of course, if they are null, they're going to be leaves, and they are initially null until you go ahead and keep adding to your tree. And of course, the constructor, you pass the data through it, set the data and set left to right initially to null, create the tree, and then we can use a simple recursive algorithm, in this case the pre-order, where we visit the root first, then we visit the left, and we find the left, go ahead and say that we found it. If not, we want to recur to the right subtree until we find it, and of course if that's false, and none of this returns true, then the node is not found. So that's a little bit more of an introductory to defining a binary search tree and actually searching for a specific node, or seeing if the node does indeed exist in the tree itself, using a recursive function or recursive method. In this case, we use the pre-order algorithm that is visiting the root first, then the left, then the right. And that's about it. Thank you guys for watching, and have a nice day.